Welcome to this class on solving problems in quantum physics of atoms. This topic is a very interesting topic. It laid the foundation of quantum mechanics. A very elementary treatment of how an electron goes around the nucleus. You can imagine it's like a planet going around the sun. It has a classical trajectory. And this is how people actually thought the electron was going around the nucleus. Now, this approximation cannot take us very far. The actual image or the actual perception of what is there is given by these wave function, or rather the probability distribution plots. The electron is really not going around in a classical trajectory, but rather it has a certain probability distribution and it can be found here or there. And as you can see in this image, this is the distribution of the electron around the nucleus of a hydrogen atom in its different energy states. So the picture is very different as compared to our classical imagination. There are no trajectories in quantum mechanics. Then, once you have discrete energy levels, what do we mean by discrete energy levels? If you consider a ball that has been thrown, or if you consider the earth going around the sun, we treat the energy of this object as a continuous quantity. It can take all possible continuum values of energy. Energy could be 2.1 joules, 2.11 joules, 2.111 joules, 2.112 joules, all continuum values. But for the quantum system, such as this atom, the energy values that it can take are discrete. So there are well-defined energy levels, and then there are transition between the energy levels. When, say, the electron absorbs some electromagnetic radiation, it can go to another level, or it can emit the electromagnetic radiation and come down to another level. And these levels are very well defined. So this absorption spectrum or emission spectrum, one can get, for example, as the one shown here below, which is the spectrum for the hydrogen atom. And then there are very well defined precise lines associated with the spectrum, such as the Lyman series, the Balmer series, the Paschen series, and so on. We'll begin by solving some elementary problems before we take up a little more difficult ones. So here is the first problem. The first line of the Balmer series of the hydrogen atom has wavelength lambda approximately 6,550 angstroms. The actual value is a little different, but for ease of calculation, I've taken this approximate value. The question says, find the wavelength of the second line of the larger frequency. Now, what does it mean, first line of Balmer series? Of course, there's a series, but how do you know where to begin with? Is it this end or the other end, high frequency end or low frequency end? So let's look at the Balmer series and how it originates. You have, these are the discrete energy levels. And as you are close to the vacuum level, the energy levels are spaced closer to each other. And then when you go to lower energy levels or to the ground state, you have larger separation between the energy levels. So the energy levels of the hydrogen atom, they scale as minus W, a constant I'll talk about later, upon n square, where n is an integer. So here we have n equal to 1, which is the ground state, n equal to 2, n equal to 3, and so on up till n equal to infinity. We are talking about the Balmer series, and where exactly is this Balmer series? Well, let me draw first for you the Lyman series. The Lyman series corresponds to transitions where the final state is the ground state. So you can have a transition like this. You can have another transition like this, a third transition like this. And these are having different frequency because the energy associated with these separations are different. And what about the Balmer series? So let's have a look at that. The Balmer series corresponds to transitions to the first excited state. So you can have the following transition and a transition from the next higher level and to the next higher level and so on. So this is the Balmer series. The question says the first line of the Balmer series. So which is the first line? Should I begin from this one, which has the shortest frequency, or should I begin from the other end? Now, if you look at the energy levels, as I mentioned, they are getting closer and closer to each other as you are going to the higher energy levels. So all of them actually have nearly the same frequency or same wavelength, and that corresponds to lambda limit. So the first line is actually defined to be the longest wavelength line, and which is this one. So we have the final state for the Balmer line as NF equal to 2. So let's apply this solution here. For Balmer series, we noted NF is equal to 2, and the N initial, that is the initial energy level, can be 3, 4, 5, etc. We are given the first line has a certain wavelength, and we are required to find the wavelength of the second line, which has larger frequency. So we will make use of this expression, which essentially originates from the fact that the energy levels scale as 1 over n squared, and E being h nu, and nu being c by lambda. So you can see, you can connect these for the nth energy level, and now we are looking at the difference of two energy levels. So from there, it follows that 1 upon lambda is equal to R times 1 upon NF square minus 1 upon NI square. So that's the general expression, and of course I should index this wavelength because this wavelength corresponds to the transitions only between these two levels. And R is your Rydberg constant. So let's solve this problem. You have 1 upon lambda 2 comma 3, and that is equal to R times 1 upon 2 square minus 1 upon 3 square, and that gives us 5R upon 36. Or let me write it here, 5R upon 36. Similarly, 1 upon lambda 2 comma 4, and what is that? That is R times 1 upon 2 square minus 1 upon 4 square. So it's the transition from n equal to 4 to n equal to 2, and that is equal to 3R upon 16. In this case, we are already given one of the lines. We are given the first Balmer line, and the wavelength of that is given to us. We need to find the other one, and we don't even need the Rydberg constant to solve. We have lambda 2 comma 4 upon lambda 2 comma 3, and this is 5R upon 36 into 16 upon 3R. and that cancelling out the terms, you get 20 upon 27. I'll write it over here. And from this, lambda 2 comma 4 is 6550 times 20 upon 27, and that is equal to 4850 angstroms. So that completes the first problem. And this line, of course, is called the H alpha line, and this is the H beta line. Now let's go to the next problem. This problem says if the first line of the Balmer series has the wavelength 6550, find the wavelength of the first line of the Lyman series of hydrogen spectrum. Now, this question is very similar to the previous one, so I could quickly go over it. You have 1 upon lambda times 1 upon lambda indexed with final and initial state is equal to the Rydberg constant times 1 upon nf square minus 1 upon ni square. And here for the Balmer series, what do you have? You have nf equal to 2 and ni equal to 3 because we are given the first line. Then for the Lyman series, where we need to find this wavelength, we are given nf equal to 1. That defines the Lyman series, this fact, like just how nf equal to 2 defines the Balmer series. And it's again the first line of the Lyman series, so it will be ni equal to 2. So we can proceed with this, and let's have a look here. This becomes 1 upon lambda 2 comma 3, and if you plug in the values, what you get? You get the answer as 5r upon 36 and 1 upon lambda 2 comma sorry, let me correct this, 1 upon lambda 1 comma 2, because now we are looking at the Lyman series, and this gives us 3r upon 4. So combining these two equations, I can write lambda 1 comma 2 is 5 upon 27 times lambda 2 comma 3, and that is approximately 1210 angstroms. So this completes the second problem, and now let's look at a different problem. The third question says, assume that the velocity of an electron in the first Bohr orbit can be defined by Bohr's angular momentum postulate. If it is defined that way, find its velocity and comment if the electron is relativistic. Now, if it was relativistic, there will be some kind of a self-consistency involved here. I'll touch upon that. But here, as I mentioned, the electron has a distribution. It has a probability distribution if you go to the more exact theory. The question says, assume that it is going around like a classical object, which it is not doing. With that assumption, you should try and find the velocity in the first Bohr orbit. And we are required to make use of the Bohr's angular momentum postulate. Certain constants are given here to complete the solution. So let us begin with this solution of this problem. As a short remark about what actually is happening in the atom is that you don't have the situation where you have nucleus and the electron going around in an orbit, right? What you have is the nucleus, and there is a certain what can say probability density certain probability that the electron can be found here or there. And when you learn advanced quantum mechanics, you will try and find it using something that looks like no, but this is for later. You will find the expectation value of the velocity operator or the momentum operator divided by mass in the first excited state. Because if it has a probability distribution, it's really not going in a trajectory. It's a good approximation to say it goes in a trajectory for certain purposes. It does reproduce some results which are correct, but does not reproduce all the results. For today's class, we will stick to the elementary theory and let's proceed with that. So in the elementary theory, you have Bohr's angular momentum postulate, which says angular momentum mvr, the magnitude of that is quantized as n times h bar, where h is the Planck constant and bar means you have to divide it by 2 pi. It is given that n is, which is the integer, is equal to 1 in this present case because we are looking at the first Bohr orbit. And we are required to find what is r, what is the radius of this orbit. So the centripetal force has to be equated to the Coulomb force. The electron is experiencing a Coulomb force from the attraction to the nucleus. They are oppositely charged. And when it executes a circular motion, there is a centripetal force. When the two are balanced, you have a classical picture. But on the classical picture, I am imposing this quantum mechanical requirement that the angular momentum should be quantized. It can only take discrete values. Right? So this is the balance of forces. And we will proceed here. So let's equate mv square by r, which is your centripetal force, and this is equal to E square upon 4 pi epsilon naught into r square. And we can proceed and write mv square r is E square upon 4 pi epsilon naught, or we can write r is E square upon 4 pi epsilon naught mv square. Right? Then the next step, so here we can write mvr as equal to E square upon 4 pi epsilon naught v, and that is equal to your nh upon 2 pi from Bohr's quantization, angular momentum quantization, or Bohr's postulate. Now we have from here all that we need to solve for the velocity. And what is the expression for velocity? It becomes E square upon epsilon naught into h. So we can plug in the values. We are already given charge of the electron, we are given the permittivity of free space, and we are given the Planck's constant. And when we do that, what do we get? We get a value 0.219 into 10 raised to 7 meters per second. So that's the velocity that the electron has in this orbit, the first Bohr orbit. This value can be seen to be approximately 3 times the velocity of light upon 137. So it's actually much less than the velocity of light. Therefore, it's non-relativistic, and it is therefore self-consistent because we never assumed it to be relativistic. It's clearly a case of non-relativistic, where your velocity is much less than the velocity of light. The velocity of light, as you know, 3 into 10 to the power 8 meter per second. This question can also be done in a different way, and the different way is if we know what is Bohr radius. So to be exact, the Bohr radius will be introduced to you in advanced courses, where you will learn that this is the place where the wave function goes to 0 as a function of r, and this is your Bohr radius r naught if you look at the solution of the hydrogen atom problem. But then it gives an idea of the extent of the size of the what you call the wave function, or the radius of the orbit. And if we take the first energy level and assign the radius to be equal to the Bohr radius, although it's actually a probability distribution, I can solve this question a little more easier. It's nh upon 2 pi mr, and if I know r, I can solve this problem and I can obtain the same answer. The Bohr radius is 0.52 angstroms. So let's go to the next problem, which is question 4 here. Collisions knock off the lowest energy electron in a helium atom and raise the remaining electron to various excited states. If the resultant helium ion is irradiated with a broadband wavelength source, that is, it contains a lot of wavelengths, then find the largest wavelength that would be absorbed. And to help us, we are given the value of the Planck's constant in different units, in joule seconds or in electron volt seconds, and we are given the speed of light. So let us see how to solve this problem. We first note that helium is the 1s2 system. It has 2 electrons, but then we have knocked off 1 electron, so it becomes He plus, and that has only 1 electron, so it is isoelectronic. It has the same number of electrons as the hydrogen atom. So the physics of the hydrogen atom, actually the symmetry of the problem, because there is only 1 electron, the symmetry of the problem is preserved and you get identical solutions, but there is a difference that the nucleus still has double the charge. And then you will write the energy levels of this problem to be equal to Z square, Z being the nuclear charge, times the nuclear the charge associated with the fact that there are 2 protons there, times the Rydberg constant 1 upon nf square minus 1 upon ni square. And Z is the number of protons. With this, we can know the transitions involved in the helium ion, which is isoelectronic. Now we are given the fact that we have to find the largest wavelength which will be absorbed. So among all the wavelengths, what would be the largest wavelength? We have written out the general expression, and let me write down this expression with the numerical values. Nf, Ni, Z is known to us, becomes 2 square, and the Rydberg constant is not given, but if we don't know, we can use the value 13.6 eV, which is the ionization potential of the hydrogen atom divided by H into C. If you look at the solution of the first problem, I have discussed that the Rydberg is actually in terms of this ionization potential divided by H times C, which comes from the dispersion relation of electromagnetic radiation, into this expression 1 upon 1 square minus 1 upon 2 square. Because we are looking at the longest wavelength, we will have to set the final NF to 1 and the initial NF to 2, and that would give us the longest wavelength. With the quantities that are given to us, we can plug it in, and we will obtain 1 upon lambda NF Ni is equal to 4.0 into 13.6 eV upon 4.14 into 10 raised to minus 15 into 3 times 10 raised to 8 into 3 upon 4, and this will be meter inverse. And let's obtain the numerical value, which will be lambda minimum will be, sorry, the lambda maximum will be approximately 300 angstroms. Now, there is another way of solving this problem, a second method. In case we know the Rydberg constant, then R is 109,678 centimeter inverse, or if I can write it in SI units, 109,67800 will approximately meter inverse. So if you know the value of the Rydberg constant, then the solution becomes much shorter. I will write NF Ni is equal to, here it is 4R times 3 by 4, or it is 3 times R. And from this you will get lambda 1 comma 2 will be 1 upon 3R, and that is again about 300 angstroms. So that completes the solution of this problem, and I will continue the solutions of the more problems related to this topic in part 2